Good morning, everybody. I hope you guys are okay. I hope you all can hear me now. Let me know if you cannot hear me. Hello? So I'm assuming you can hear me. Thank you. People can tell me. So before we talk physics, I wanted to talk about a couple of other things. So I'm going to switch what I'm sharing here to this one. Okay. So first, I wanted to talk to you a little bit about academic integrity. So as you heard in the announcement I made, somebody posted our first homework assignment to Chegg, which is one of these note sharing, quote unquote, study websites where experts can answer your questions. And this is not an acceptable thing to do for any assignments in this class. It's not acceptable for homeworks. It's most definitely not acceptable for tests. It constitutes submitting someone else's work as your own, which is not allowed. It's fine to work with other students, but even when you work with other students, you should be submitting your own work created by yourself. Okay? That's very important. So please go and read these documents that I've posted here, the one on unauthorized use of note sharing websites. It also mentions that you're not supposed to upload anything from a class. Okay, that's a violation of my copyright to upload tutorials, especially homework solutions and test solutions. I've found quite a number of my homework and test solutions online over the years, and I've had to submit a lot of takedown requests. Okay, so please don't do that. And then please also take a look at information about the Zoom invigilation of our tests, okay? Because that's what we will be doing next Friday. So, and hopefully everybody knows that our first test is next Friday. It is during class time. And also check out this really nice video that a faculty member from, I think it's from the Beatty School, created talking about the long-term costs of cheating. So because I decided to make that first written homework for practice, you don't have to submit it. But I would advise that you go ahead and submit something. We're not going to mark it, but just to practice submitting to Canvas to make sure you don't have any problems, okay? So the other thing that you're going to have to do before the test next Friday is I've created this Canvas practice test. A lot of you have found it already, okay? And as part of that practice test, it asks you to submit a selfie of yourself holding an ID of some kind, a picture ID, so that we know what you guys look like for when we invigilate via Zoom, so we can make sure that the person registered for the course is the person taking the test. All right, so, and I know not all of you have your SFU ID cards yet, so if you don't have an SFU ID card, then please use something else with your full name and your photo. So a passport, a driver's license, something like that, okay? We'll be fine. All right, let me see if there were any other questions. Yes, basically anything with your name, your full name, and a photo. And we will also be having you put your names into Zoom so that we can match names to faces. Okay, so yes, the test is on Friday. Is going to be monitored in Zoom, and I'll give you more information about that next week. You won't be given formulas, so I would advise you to make up your own formula sheets. Making up your own formula sheet is a great way to study for one of these things. You can use your notes, you can use the textbook, you just can't use anything else. You can use whatever we have in Canvas that's visible at the time. I might hide some things, so don't count on everything from Canvas being there, okay? But generally, you can use your own notes. You can use my posted lecture notes. I'll leave those up, so you can use these. Okay, but the main thing to realize is you're not going to have a lot of time. You're only going to have 40 minutes total for a test that was designed to take 30 minutes. So looking things up Okay, just spending a lot of time looking things up is not a good use of your time. Okay, you really want to have created yourself a study sheet of some kind with formulas and hints that you can access quickly. Yes, you can use an online quadratic formula calculator, that's fine. And the test is going to cover chapters 2 and 3. So up through everything we do today and up through the second sapling homework. Okay. Yes, you should. In Canvas, you don't do units, okay? But in CrowdMark, you should always do units. So anytime it's written work, you have to show units, okay? But not for Canvas. Canvas won't let us input units, only numbers, okay? So it looks like there's a few more questions. And then just another reminder, please, 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 if you have a general question, put it in Piazza. Don't send me an email for a general question. If you have something specific to you and no one else, okay, about your personal situation, then send me an email in Canvas, okay? Not, I'm gonna, at this point, stop answering emails for general questions that show up in my regular email, and especially general questions that have already been answered in Piazza, okay? Because I just can't keep up with it otherwise. All right, so now we're gonna talk some physics, okay? So yes, you will basically, for part marks for the test, you will be submitting your work for a numerical question to get partial credit. All right, so now we're going to talk about some physics. If you have any more questions, you can come to office hours, or like I said, put your questions in Piazza, and that way I can answer them or someone else can answer them for you. Okay, and I don't know how many questions yet. I will let you know once I've created the test. So, oh, and by the way, I did post a couple of practice midterms so that you can have a look at that. Those midterms cover more than what your test will be on, and those were designed to be about an hour long to give you an idea of length. All right. Okay. So now we're going to talk some physics. Okay. So I quite like this Calvin and Hobbes comic because it's about, well, first of all, it's about an old-fashioned record player. I don't know how many of you guys have one of those. They're kind of, some people are, they're kind of coming back in again now. But all about basically what happens when you're on a record and you're moving in a circle, and how the speed is not the same. It depends on where you are in the circle, where you are on the record. Okay, but so that's circular motion. But before we do circular motion, I wanted to do one more projectile motion. I wanted to do one of my favorite projectile motion problems. And before we do it, we're going to start with a poll. So let me set up the poll here. And we'll do this one quickly. So let's start the poll. There we go. Okay. So the question is, you're a vet and you're trying to shoot a tranquilizer dart into a monkey who's hanging from a branch in a distant tree. You know that the monkey is very nervous and will let go of the branch and start to fall as soon as your gun goes off. In order to hit the monkey with the dart, where should you point the gun before shooting? So do you want to point your tranquilizer gun right at the monkey, below the monkey, or above the monkey? That's the question. This is a very classic projectile motion problem, so you may have run into it before. Hopefully there's a pillow at the bottom or some bushes or something for the monkey to fall into so he doesn't get hurt. All right, I think we will end this one in 10 more seconds. So if you're not sure, go ahead and guess. This is just a tranquilizer dart. Okay, we're not going to hurt the monkey, so don't worry about the monkey. It's a vet, right? The vet's trying to treat the monkey. Yes, ignore air resistance. All right, so 5, 4, 3, 2, 1. All right, let's have a look at the responses. Okay, so it looks like 137 people, which is the biggest group, think the answer is B, below the monkey. And then the next biggest group is A, right at the monkey. And then we also have a few above the monkeys. Okay, so let's get rid of the poll now, and let's see how this works. All right, so what we're going to do is use two-dimensional kinematics to figure this out. Okay, so in a minute, this will pop up for you guys. So here we go. So I've started again, as always, by drawing a picture. So here's our XY axis, and I've decided to put have the dart start at x equals 0, y equals 0. That's our initial position. Yes, I know that's a gun. I didn't have a tranquilizer gun. That's actually a sort of like a cowboy gun there. Anyway, so we're going to have the dart start at 0, 0 with some velocity v0. And the velocity vector makes an angle theta with the horizontal. Okay. And the monkey's going to start a distance horizontally d away, okay, and add a height of h. Okay, and this monkey, remember, is dangling in the tree. I didn't actually draw the tree. Okay, and the question is, okay, so in this scenario, we're aiming right at the monkey. And so we're going to try and answer the question, if we were to aim right at the monkey, okay, is this the right launch angle such that the dart will hit the monkey? Or do we have to, in fact, aim higher or lower than this? So this is the straight at the monkey launch angle. Okay, so the requirement is, all right, that if the dart's going to hit the monkey, the dart must be at the same y position as the monkey when the x position of the dart is d. So when the dart gets horizontally over to d, its y must equal the y of the monkey. Okay, so what are we going to do? We are going to start doing our kinematic equations. So we're going to start with position as a function of time. These are in the vertical direction, in the y direction. So that's our kinematic equation. And we're going to first look at the equation for the y position of the dart. All right, so the dart starts at y0, 0 equals 0. So we plug in 0 for that. And then we're going to leave everything else symbolic here. So we have just v0 yt minus 1 gt squared. That's the position of the dart as a function of time in the y direction. Okay, now here is the position of the dart as a function of time in the x direction. Okay, so the x position, all right. And so again, we know that the dart starts at x equals 0, so x0 equals 0, all right. And we also know that at the time we care about, all right, that the x position of the dart is d. Okay, that's the time we're going to be looking at. So we plug in x0 equals 0, so we know that d equals v0 x t, where t is the time when the dart gets to the horizontal position. Okay, now let's look at the monkey. So over on the other side, so what is the y position versus time look like for the monkey? So the monkey starts at height h, so y0 equals h. So we plug in h there. The monkey is falling from rest, so v0y for the monkey is 0. So we lose the second term, but we still have minus 1/2 gt squared for the monkey. So there's the position of the monkey as a function of time in the y direction. So now we're going to set them equal to, right, each other, because we want the dart and the monkey to be at the same y. So we're going to set those two equal to each other. We want y of the monkey to equal y of the dart, okay, at the time given. If that's true, okay, then this was the right angle to fire. Otherwise, we should be able to figure out whether it should have been higher or lower. All right, so we're going to plug those two equal to each other. All right, so there's y monkey set equal to y of the dart. And hopefully you notice that on both sides of the equation, there's a term minus 1/2 gt squared. Okay, both the monkey and the dart are basically accelerating in a negative y direction. And so they're both have that minus 1/2 gt squared term. So that means that term cancels out, right? And since it shows up on both sides of the equation, you could add plus 1/2 gt squared, right, to one side of the equation, and the whole thing would cancel out. All right. So if someone has a question, they have their hand risen. Hopefully Rasul can answer that question. So what do we get? We get that means that h must equal v0y times t. Okay. And then what we're going to do now is go back over to the left-hand side and solve for the time, okay, when the dart gets to x equals d. So that time is d over v0x. And we're going to plug that in for t over on the right. So we're going to plug that in, and we get this expression, okay? We get h equals v0y d over v0x. All right, and then if we rearrange that ever so slightly, we get this expression. So what did we see? We see that for these two y's to be the same, okay, for the monkey and the dart to be at the same height, when the dart is at x equals d, that requires that h over d be equal to the ratio of the y velocity, the y component of the velocity, to the x component of the velocity, which, as we also know, is equal to the tangent of theta, the launch velocity angle. Okay? And then if you look at it and you think, oh, look at that, right? The what's going on here is that if we want the y component and the x component of the velocity to have the same ratios at h over d, right? Then basically we're talking about them two similar right triangles. Okay, in other words, the angle that the right triangle makes, right, that angle with the horizontal, okay, with a height h and a width d, right, that angle has to be the same as the angle the velocity was launched at. The two angles have to be the same in order for the dart to hit the monkey. Okay? And so basically the result is that the dart must be pointed directly towards the monkey, okay, in order for it to hit the monkey. Okay? Because we need those two basically y over x values to be the same. Okay? If they are the same, then the two y's will be the same. Okay? So another way to think about this, all right, is to think about what happens when the dart moves. So say you did fire that dart along that green dotted line. And what happens over time, as some of you were saying in the chat, is that the dart starts to fall away from that path. And as the dart falls away from that path, the monkey also falls. And so you can see them falling the same amount in the same times. And so when they get to D, they'll both be at the same height. Okay, it's because both objects, right, are undergoing that same y acceleration, the same acceleration in the negative y direction. So essentially, they both fall the same amount. Okay. So yeah, that's not a very strongly powered dart gun here. So I wanted to show you this. So the answer is right at the monkey. Okay. Yeah, you need those two angles to be the same. Okay. You need to fire right along the line that goes straight to the monkey. So there are a lot of really nice video versions of this online. This is one of them. Okay. And I am going to play this for you. And hopefully you'll be able to see it. If you can't see it very well, you can try and go find it if you Google shoot the monkey. So let's see how well this works. And I've given you a YouTube link there too that you can give a try to. So let's see if this is going to work this time for me. So this is Shoot the Monkey starring Daniel. So here's Daniel. He's got this great hat, does Daniel. Okay, and he's got a laser there. He's going to use a laser sight, okay, so that he knows that he's lined up with his monkey, that he's really aiming right at the monkey. Okay, there's the monkey cam. It's a tranquilizer dart. They're not hurting the poor monkey. So there's the laser. There's the sight. So right in the middle. And now he's loading his tranquilizer gun. And there's the monkey. That's what our lecture hall's. Whoa. So, okay, so that was the monkey version, but it's hard to see what's going on here. So he's going to fire it from a different view. And there you can see that the ball hit the monkey, that the ball and the monkey both fell the same amount. And this is another view. And then they play around with a slightly different ball speed. Here's a lower speed, so the monkey falls further because there's more time. And I have put a link to this in Canvas for you guys to see. There goes the monkey. Okay. So the size of the dart doesn't matter. Okay. The speed, as long as the dart gets to the monkey. If you fire the dart too slowly, it'll hit the ground. I've had that happen live. Okay, where it just hit the ground before it got to the monkey. Okay, so that's so the famous shoot the monkey problem. Okay, and you can see that we solved that using our two-dimensional kinematic equations. Well, the velocity only matters in that the dart has to get to the monkey and not hit the ground first. Okay, and it doesn't depend on the monkey's mass if we're ignoring air resistance. So, okay. So now we're going to move on from projectile motion. And let's see if I can get this to switch. Sometimes this doesn't want to switch for me. There we go. And now we're going to do the uniform circular motion. So that was the other topic in the pre-lectures. It's the last topic we're going to cover in chapter 3. So what is uniform circular motion? Uniform circular motion is motion along a circular path at a constant speed. Okay, so what does that mean in terms of velocity? That means that the magnitude of the velocity will be constant. Constant speed means the magnitude is constant, but the direction of the velocity is not constant. Okay? So let's have a look at what that looks like. So here is a picture of a circular path, and you have to imagine an object moving in a circle, okay, around that path, along that path, and we've got an initial velocity v0, so it starts to the right of the center of the circle, and then it moves up to the top. Okay, so the final velocity is pointing to the left. The initial velocity was pointing up. The final velocity is pointing to the left. So you can see the direction of the velocity has changed. And we know how much the velocity of direction has changed. We can look at delta v, the change in velocity, which as we've seen a few times now, is always the final velocity v minus the initial velocity v0. And so you can see which direction the change in velocity points. Okay? It points downwards and to the left here. And if we were to take that change in velocity vector and stick it halfway between the starting point and the ending point, okay, and because that's basically sort of the, on average, the change in velocity, right? That's the change of velocity between those 2 points, right? You can see it points to the center of the circle. Now we can do the same thing for a smaller time change or a shorter part of the path. Okay, so now V0 starts again the same way straight up, but now the final V is at an angle, right, to the upper left. And if we do this basically again, calculate change in velocity, we have the final velocity V minus the initial velocity V0, and we get a different vector for delta V. Okay, it hasn't changed quite as much and it's a different direction, right, because we're talking about a different time change here. Okay, and again, if we put that change velocity vector halfway between the starting point and the ending point, again, the change of velocity points towards the center of the circle. Very interesting. Okay, in fact, you can try all sorts of different combinations and you'll always get a vector that if you put it halfway between the two, okay, it will point towards the center of the circle. Okay, so what does that tell us? So delta V, well, it tells us the direction of the acceleration, right? Because delta V always points in the same direction as the acceleration. Okay, so that means the acceleration will look like this. So I've drawn in a couple of acceleration vectors in yellow. Okay, so, and that means that for uniform circular motion, the acceleration will always point towards the center of the circle. And we have a special name for this acceleration. It's called the centripetal acceleration. It was coined by Newton. Centripetal means basically center seeking, pointing towards the center. And it has a constant value if you're moving with a constant speed. If you're undergoing uniform circular motion, and that constant value, which they derived for you in the pre-lecture, is equal to the speed squared, or the magnitude of the velocity squared, divided by the radius r of the circular path. Okay? So, right? So this is the magnitude of the acceleration vector. Okay? AC here. All right? And like I said, it's called centripetal acceleration. All right. So yeah, and the way they derived this, way they calculated this, was to actually calculate delta V over delta T. All right, so let's do another poll question. See if we get the hang of centripetal acceleration. All right, so this has got 5 choices. Okay, so we'll start this one going. All right, and the question is, as the ball passes the point shown, so we've got a ball moving counterclockwise, okay, so at the point shown, okay, the velocity is up and to the left, and we've got an XY coordinate system drawn in here, off on the side, okay, where Y is up and X is to the right. And the question is, as the ball passes the point shown, the Y component of its acceleration is negative and becoming more negative. So we're looking at the Y component now. So the component along the Y-axis. Okay, so because remember, acceleration is a vector, so it's going to have components. So is the Y component negative and becoming more negative? Is it positive and becoming more positive? Is it positive and becoming less positive, or is it constant? Okay, and we particularly want to know what's happening to the Y component. So I'll let you think about that one for a little while. So think about which way the acceleration is pointing at this point, where you can see the ball, and think about which way the acceleration would point later when the ball has moved some. So as it's passing the point where it is, okay, where it's shown. So in other words, draw the acceleration vector where it is now, pick a point in the future where the ball will be, draw the acceleration vector again, and look at what happened, okay? Just slightly different. So don't draw very far in the future, but just a little bit in the future, and draw the acceleration vector again, and think about what's happening to its y component. Oops. Yeah, essentially what's happening at this instant. Okay, we know the acceleration direction is changing. I'll tell you that. So I'll give you that. Okay. All right, I think we're going to do maybe 20 more seconds. I'll set my timer. Okay, 5, 4, 3, 2, 1. Okay, so let's have a look at the answers. So there's a lot of disparity, okay? So a lot of disparity here. Maybe it's the wording of the question that's slightly confusing. So let's have a look at the answer, and I'll show you what I was trying to ask here. All right. So basically, we want to know what's happening. So first, we need to know where the acceleration starts. Okay, so that's where the acceleration starts, right? Pointing towards the center of the circle. Okay. So, and then later on, okay, it looks like that. Okay. And so what is happening to the y component, okay, is that it's negative. It's in the negative, it's downwards. It's in the negative y direction. And it's getting bigger in the negative y as it travels, right? Because at this point, the y component is smaller than the total magnitude, right, of the vector. Whereas when we get up here, the y component is equal to the total magnitude. So that's a bigger y component, okay, in the negative direction. So what's happening to the y component? Okay, it's negative. It's in the negative direction, and it's becoming more negative. Okay? That makes sense to everybody? Okay? Right? Yeah, whereas the x component is negative and getting smaller, right? Getting less negative. Okay? So the, yeah, the x, y coordinate systems are in the corner there. Okay? So I think we're going to move on from there so we have time to do everything else. We can come back to this at the end if there are more questions. All right, so what else is useful to know about uniform circular motion is, okay, calculating values for uniform circular motion. Okay, so if you go once around, right, then we know that the total distance you traveled will be the circumference of the circle, which is 2 pi r, and we give a special name for the time it takes to go around once. We call that capital T, the period. Okay, therefore, the speed then for an object in uniform circular motion, remember this is a constant value, is equal to 2 pi r divided by t, or the distance over the time. Okay, and now we can use that to write a different expression for the centripetal acceleration. So we can take our centripetal acceleration equals v squared over r, and we can plug in for v our 2 pi r over t, the period, time to go around once. Okay, and of course squared. And then we notice now we have an r squared on top, and we have an r on the bottom. So one of those r's will cancel out, and so we can also write this, I lost my mouse, as 2 pi r over t squared times r. Okay, and so you can see that the centripetal acceleration is proportional to r. Okay, so for an object with a given period. Okay, so that's important to remember. That's for an object with a given period. All right, so I thought we would have a look at this real quick with one of our PHYS. Okay, this is an old PHYS, so it's a little hard to see this one, but this one's called Ladybug Revolution. Okay, I'll see if I can find this now. This is one of my favorites from a long time ago. Why can I not find this? Oh, here it is. I think this is it. Okay, so this is a ladybug, and I think it's supposed to be a ladybug on a on like a record player. Okay, and I'm going to start my ladybug going. So there's my ladybug going, and you can see, I know it's a little jumpy, but you can see the ladybug's velocity and acceleration vectors. Okay, a little jumpy there, but you can see the green vector is the velocity and the red vector is the acceleration. Okay, all right, so I'm going to pause the ladybug for a second so that you can see the velocity there. Now it'll clear up a little bit. You can see those a little bit better. Okay, so then I can take my other bug, I don't know what kind of bug this is here, right? And I can put it, I'm going to pause for a second. It starts moving. Okay, so now I'm taking this other bug and putting it further away from the center. Okay, but remember, both of these guys have the same period. Okay, both of them are traveling, right, taking the same time to go around once. Okay, though the big bug here, whatever this guy is, I don't know if he's a cockroach or a beetle or what he is, okay, he has a bigger speed, right, because he's doing a bigger circle, okay, in the same amount of time, right, and the ladybug is doing a smaller circle in that time, right, when you go around once, okay, so the ladybug has a smaller velocity and a correspondingly smaller acceleration. So I'm going to move this guy out to the outer edge a little bit. There we go. And so you can watch them. And so you can see, okay, how the velocity depends on how far away you are from the center of the circle. Okay, and you can see that the acceleration depends, okay, from how far away you are from the center of the circle. Okay, for two objects, right, on a turntable or of some kind. So this is a good thing to remember for the future, because later on in this course we'll do rotational motion and we'll define rotational variables, and we will look at cases where things are moving in circles like this. Okay, and have this basically and have the same period, take the same amount of time to go around once. Okay, there's lots of scenarios like this, things in centrifuges, anybody on a merry-go-round, anything like that, Ferris wheels, stuff like that. Okay, so we're going to stop that. And we're going to go back to our PowerPoints. Where are we here? Okay, so there was our math. Okay, so we've got another clicker question to try, another poll. So we will try this one. Okay. So have a look at this while I put in the choices. Okay, so what's going on here? So we have two children, Henry and Maya, or Henri and Maya, and they're riding on a circular merry-go-round that spins at a constant rate. So this is like our bugs, okay, our ladybug and our beetle. Okay, so Henri is at the outer radius, like the bug, okay, the beetle, sorry, and Maya is like the ladybug. She's halfway between the outer radius and the center of the circle. And the question is, what is the ratio of their centripetal accelerations? Okay, so we're looking for the ratio. So basically, if you were to take Henri's centripetal acceleration and divide by Maya's centripetal acceleration, what number would you get? So think about who would have a bigger centripetal acceleration, Henri or Maya, in this scenario? And then how much bigger or smaller would that acceleration be? And you have to think about what I showed you on the last slide. Do you want me to go back to the last slide for a second? Yes, okay. So I'm gonna see if I can do this. There's the last slide. You may have to hide your poll for a second. You can click on the little X in the corner and it'll hide the poll. Okay, so now I'm going to go back forward. So hopefully everybody saw that. Go back to the question. Okay, we're not assuming their velocity is the same. We're assuming that they're on the same merry-go-round, so their period is the same. The time it takes them to go in one circle is the same. In fact, their velocities are not the same, right? The one that's Maya, who's only halfway, will have a smaller speed than Henri, who's further out, because Henri's path has a bigger radius. Right? Because if you go back one more time, we can see that the speed, right, depends on the period and the radius, 2 pi r over t. So bigger radius, bigger speed. Okay, I think we're going to finish up here because we've got one more thing to do after this. So we will do 10 more seconds. So if you're not sure, go ahead and guess. Yes, so traveling in a circle with a larger radius and making the same number of revolutions per time means a greater speed. Yes. In fact, that's the thing that blew Calvin's mind in the comic we looked at the beginning. Okay, so let's do 5, 4, 3, 2, 1, and let's look at the responses. So it looks like the largest group voted for B, that Henri's acceleration should be 2 times bigger than Maya's acceleration. So let's have a look and see. So there's that equation we had on our previous slide, right? So we have, and this is the one I derived, it depends on radius. And so we can see, so what I did was I plugged R in for Henri's radius, and I plugged R over 2 in for Maya's radius here, okay? And then I just took Henri's acceleration divided by Maya's acceleration. And what happens is almost everything cancels out. Okay, the 2 pi over t squared cancels out, and so you just get, and then you have r divided by r over 2, which is essentially equal to 1 over a half, which is equal to 2. So the answer is 2 here. Okay, so Henri's acceleration is twice the magnitude of his acceleration is twice the magnitude of Maya's. Okay, so I wanted to finish up real quick with an example problem. It's kind of a fun example problem. It's about what's called a geostationary satellite. So geostationary satellites are satellites that stay in the same spot above the surface of the Earth as the Earth rotates. And what that means is that they have to have the same orbital period as the time it takes the Earth to spin on its axis. So once every 24 hours. So our geostationary satellite has an orbital period of 24 hours and an orbital radius. In order for this to work, okay, your radius of the circle has to be 42,164 kilometers. It's an enormous number. Okay, so first question, how fast is the satellite moving? So we just do 2 pi r over the period. So 2 pi times, you'll notice I converted my kilometers to meters. So that makes it 42.164 times 10 to the 6 meters. And then I'm dividing by, I want to get this in meters per second. So I'm converting my 24 hours to seconds by multiplying by 3,600 seconds per hour. Okay, and if you do that math, you end up with 3,066 meters per second. Okay, yes, you do have to convert these things. And since I was given 24 hours only has 2 sig figs, the answer to 2 sig figs would be 3,100 meters per second. And then now we've got v, we can figure out its centripetal acceleration. So we just do our v squared over r, or 3,066 meters per second, divided by the radius in meters. And you definitely want to convert everything to meters and seconds, and then you'll get an acceleration in meters per second squared. And so you get quite a small acceleration, okay, for these satellites. By the way, this picture is the very first geosynchronous satellite that was put into orbit around Earth. Okay, it's kind of a cool looking satellite, I think. Okay, so, and then you can also do it with the other formula. So I wanted to show you that the other formula gives you the same answer. Okay, so if you plug in now the period again, so 2 pi over t squared and multiplied by the radius, you will get the same answer, that the centripetal acceleration for our geostationary satellite is 0.223 meters per second squared. So that's a way to check your answer, is you can try the other formula. That's always, if you have more than one formula, it's always a good idea to check your answer, because then if you get the same answer both ways, then you know you did it right. Okay, so that's where we're going to end today, is right there. Okay, so, but if anybody has any more questions, I'm happy to try and answer them. So would it make sense to say that for the circular pole question, the AC is negative and becomes more negative? The Y component is negative and becomes more negative. Okay, the AC itself is not. Okay, AC, you wouldn't say a vector is negative, but you could say a Y component is negative. Okay, so because so the velocity is negative, but it doesn't keep getting negative. Let me think about that. No, I guess the let me think about that. Let's go back to that one. So I have to go back to that one. Yeah, I think that would be okay to say, because it's true that we have a negative component for the velocity at the first point, and when you get up here, the Y component, sorry, the X component. Okay, so the thing you have to be careful about is that's in the X direction. Okay, I mean, the way to figure out what the acceleration is doing here, of course, would be to look at delta V, the change in velocity, like we did earlier with when we first started looking at circular motion. So actually, while I'm thinking about this, I'm going to stop recording.